All right, so this is our work and power lesson. We are going to talk about work and power before we actually calculate our own work and power in the Powerhouse Lab. So for students that are absent today and need to do this lab from home, you can definitely do this lab from home using a scale in pounds, converting it to kilograms, a timer on your phone, and a ruler to measure some steps in your house. Doesn't have to be a ton of steps, just a few steps to measure a change in height. So before we start, let's talk about work. Work is a is the amount of energy transferred, and it is by applying a force through a parallel distance. So when I say parallel distance, it means that the direction of the force that you are applying is going to move the object in a distance that is in the same, that is parallel to it. Not necessarily the same direction, but if I were to push a table, the table would move right if I were pushing it right. In the sense of friction, friction can also do work, and that is if you are pushing let's say a box across the floor. Friction is applying a force opposite to the direction of motion, but the direction of motion is still parallel to that force. So anything that does work would be applying a force and moving an object in that direction, or in the case of friction, opposite of that direction. So things that generally do work is chemical energy, which you would think of as energy from a person, a motor, or a battery. And the equation for work is force times distance. The unit we use for work is joules, because work by definition is a change in energy. And so work is going to have the same units as the unit we use for energy. So joules is our unit for work. Power, let me skip this video. Power is the rate in which work is done. The faster you're able to do your work, the faster you're able to push an object a certain distance, the greater your power value. So power is work divided by time. Since work is force times distance, you can think about it as force times distance divided by time. And the unit for power is watts. You've heard the unit watts before. It's something that we use to measure electricity. Maybe when you get your electricity bill, you've seen the unit watts in it. And unfortunately, it's represented by a capital W. It's the same variable we use to represent work. So I encourage you to spell out watts when you're writing out the unit, so that you don't get work and watts confused. Okay. Let's think about proportions. Obviously, if you increase your force or the distance in which you are moving something, you are increasing your work and therefore increasing your power. Power and work are proportional to each other. The more force you exert or the more distance you move something, the more power you have. But it is inversely proportional to time. Meaning as time increases, power decreases. They are opposite of each other. So what you want to increase your power is to reduce your time, because as time goes down, power goes up. And so our goal in the Powerhouse Lab today is to figure out how we can race up those bleacher steps, or whatever steps you have in your house, trying to do it in as little time as possible, but also safely. So the Powerhouse Lab, we're going to be running up a set of bleachers. So I want to think about what our LOL diagram would look like for that. First of all, our system is just going to be your body, you who are moving up the steps. And when you think about where you're going, you start at the bottom of the bleachers, you end at the top. It's easiest to do the final energy, which would be gravitational potential energy, because now at the top of the bleachers, you've got a height. So this is GPE. But where did that height come from? How did you get there? You got there by using energy from your body. Now, generally, we would put chemical energy in our diagram, in our bar chart, but from this point on, I want you to think of any sort of chemical energy as energy being put into the system. And you want to make sure that your system is balanced. So if I put 2 joules of energy in, this is chemical energy from my body, then I get 2 blocks of gravitational potential energy coming out. Based on conservation of energy, they have to stay the same. Now, let's think about the fact that work is equal to force times distance, and it's also equal to change in energy. Well, this change in energy right here is gravitational potential energy. And my gravitational potential energy is going from 0 to 2 blocks. I don't know how much that is yet, but I know that this is my change in energy. It is a change in gravitational potential energy. So force times distance is going to equal my change in gravitational potential energy, mg, and I'm going to put delta H here. And the reason why I'm putting delta H is because work is a change in energy. And a change in energy means that I need to be changing height when I'm talking about gravitational energy. Obviously, mass can't change. Gravity is still on Earth 9.8. So the only thing that can change is height. Now, I want you to think about how force times distance and mass times gravity times height could possibly be equal to each other. Well, first, distance and height in this scenario mean the same thing. We're moving our body a height above the ground, so they both are measured in meters, so that could represent our distance. That leaves the remaining variables to represent my force. So this right here, mass times gravity, is equal to force. It actually is a force equation that we've calculated many times. This is the force of gravity, or the force of Earth, on an object. So when we talk about the force of Earth, mg, we're also referring to our weight. So I'm not going to spell it out because it takes too long to do that, but this is our weight. Actually, let me just finish spelling it because I don't want to leave it as W because we already used W so many times, but I want you to understand that the force that is being moved is our weight, and it is moved a height above the ground when we walk up the bleachers. So you're going to use all of these concepts to complete your Powerhouse Lab. For those of you who are at home, I want you to look at your Powerhouse Lab. You are going to do these trials on your own. These are just the basic concepts we covered in class. Your mass, generally when we weigh ourselves in pounds. You're going to have to convert your weight in pounds to kilograms. You can Google that pretty easily. You want to measure the height, not the diagonal distance in which you're walking up the stairs, but the physical vertical height of your climb. And you're not using the top of the bleachers, but if you have stairs at home or even a few steps up to your porch or anything like that, you can use those steps and measure the height of that. And then last but not least, you are going to take your UG. This is actually representative of gravitational potential energy, so just substitute that with GPE. Same thing with this variable right here also. UG represents GPE. You are going to calculate your gravitational potential energy. Remember, gravitational potential energy represents work because it's a change in energy here. And so once you calculate or measure the different time it takes to get up your steps, you can take your gravitational potential energy or your work and divide it by the individual time values. Your goal is that for each trial, you decrease your time and therefore increase your power. After you've done that, you're going to complete the follow-up questions. Make sure you do this before you check your answers at home. There are some conversions here you want to think about, like watts to horsepower and minutes to seconds. And then you want to go back to worksheet 2 because we only completed the first 4 problems of worksheet 2. We actually completed only half of problem number 4 last class. And so once you collected your kinetic energy, you can use your work equation to solve for the distance in which the bullet is penetrated. That's your D value in work equals force times distance, and you've got force right here. The rest of this is going to pull our energy calculations and concepts into some force body diagrams. It brings us back to coefficient of kinetic friction, which is something we learned back in our first unit. There is a bunch of reminders here. So they tell you the equation for friction, which is mu times N. Again, mu is your coefficient of kinetic friction, so it's 0.2. N is represented by normal force. So go ahead and do those calculations. You want to complete worksheet 4 and the Powerhouse Lab along with the follow-up questions before next class. The answer keys, like I said, are posted, so you want to correct them, make sure you understand them. And then the homework on Canvas is more practice on energy conversions or energy conservation problems. So homework 5-8. Next class, I will not be here. So we've covered everything we need to cover. All you need to work on is your review worksheet. So you will have that in class on Friday, and the substitute will have an answer key for you to check your answers. If you have any questions, feel free to contact me before the test, and the test is on Tuesday. So study up, make sure you understand the roller coaster problem, make sure you understand work and power, the spring worksheet that we did, as well as obviously LOL diagrams. And there's also, as I emphasized before, a problem that is going to be related to experimental design. So you want to think about all the different objects we've used in our experiments, the features they have, how we can get velocity and height and time from each of those. So good luck. Let me know if you have any questions. And like I said, I won't be here Friday, but contact me if you have any questions on anything.